This brings us to the rest of the circuit. At this node, we have our 3 kilohertz square wave. That is symmetric between 3.3 volts and negative 3.3 volts, and oscillates, of course, at 3.3 or 3 kilohertz. This clock chip is not meant for driving large loads. What that means is the current output is relatively small and really should not draw current from it, as this then affects the output. To remedy this, we pass our signal through a unity gain amplifier before it goes into our water at node A. So now, as we've drawn previously, our square wave has been injected at node A. And of course we have the other 3 nodes here, M, N, and B, going downhill in our voltage gradient. I've laid out this schematic similarly, where we have A is at the highest point, M, N, B in descending order. Next up, our signal has been injected up here, and we need to figure out what our differential voltage is. Every single input has a unity gain amplifier. What purpose does this serve? This buffers the high impedance from the low impedance. Now, if I were to directly connect this electrode to our voltage comparator, this will draw current from our solution and therefore affect our measurement. As the solution that we're trying to measure has very high impedance, any change in current is going to enact a dramatic change in voltage, which we don't want. To remedy this, we add these unity gain amplifiers. If I draw current at the output of this amplifier, for example, it does not affect a change at the input. And so for that reason, all of our inputs are buffered. The next step in comparing voltages M and N is we use a voltage subtractor. This essentially compares the 2 square waves and finds the difference between them at any point in time. The output of this amplifier goes into a switch. And this switch is controlled by our sample trigger that we've already generated, is the output of our AND gate. So, when this AND gate, both inputs are true, and we get a true output, this switch closes. That's going to be easier to see.
Yeah, just don't draw on the screen. I've done that. I've drawn on the projector screen.
Close with the pen. Put it over here. Now, getting to the same stage at the B circuit, this is our current measurement. We generate any current that flows from A to ground is going to generate a potential difference across the shunt resistor. The output of the shunt resistor goes into a unity gain amplifier. This separates high and low impedance, and then goes into the switch. This node does not need a voltage comparator, as we were just measuring one voltage value at some point in time. So then, when we have a sample trigger that gets generated, both of these switches go from the open position to the closed position for the length of time of the pulse. In this case, the pulse is very short. I'd have to look to see exactly how long, but we're talking the order of microseconds. Now, the sample and hold part, we want to take, suppose we have a transient voltage. Say I don't know, a sine wave or some other arbitrary voltage pattern. I can draw any wave that I want on the screen. The objective of the sample and hold circuit is we want to say, okay, at a certain time, we want to sample what the voltage is, and we want to be able to hold that voltage so we can record it. So let's say this is like the input to an oscilloscope or some other device, and I take voltage measurement here. And let's say this voltage measurement is like 1.6 volts. I want to hold this voltage for long enough time that I can measure it. So what I'm going to do is I'm going to sample this voltage, and I'm going to put my 1.6 volts into a capacitor. And then I'm going to connect the output of that capacitor to an ADC. So right at this instant, I can sample my 1.6 volts, my capacitor voltage will be charged to 1.6 volts, and I can measure that 1.6 volts at an ADC. And the important part of this circuit is we need this sampling to be almost instantaneous. If I'm sampling a longer period of time, and I close my switch for a longer period of time, the voltage across my capacitor is going to start to follow the curve of whatever wave I'm measuring. And then am I really sampling this point? Well, not really, because in reality, the voltage that I'm sampling is the voltage across the capacitor at the instant the switch is opened. It's not the instant I close the switch, it's the instant that the switch opens. So I need the switch to open at a time that I decide. In this case, we're using a square wave. I have my 3 kilohertz square wave that I've drawn a million times. I'm sampling my voltage right here, and this is the instant that my switch opens. With a very short sample pulse, it's kind of irrelevant because the pulse length, the magnitude is probably 1,000 times smaller than the wave itself. But I want to capture the voltage at this point and store it in a capacitor. And to do that, I have a switch and a capacitor. It's pretty straightforward, really. At this instant in time, at the peak of my square wave, 2 voltages are induced here by the voltage gradient. They're compared. The difference between them is present on this node. And then at the instant my sample trigger fires, this voltage, the output of my voltage comparator, gets induced across my capacitor. Right here. Afterwards, my switch opens again, and this capacitor is going to retain the voltage that I've injected on it for some amount of time.
Related to the value of the capacitor?
Correct. You will notice that I don't have a pull-down resistor of any sort, and you would think typically an RC circuit is going to have a pull-down resistor. You have to have a resistor and a capacitor in series, one in series and one in parallel with ground. But in this case, all we want to do is capture the voltage at this output node and feed it to an ADC. Similarly to our inputs, our outputs also have unity gain buffers on them. The reason for this is when the ADC does when the ADC samples the voltage, it draws some current from the source that it's measuring. And if I were to connect this capacitor directly to my ADC, the ADC would drain all of the charge off the capacitor. This isn't good for our measurement, as now our ADC is influencing the value that we're reading. To prevent this, we put a unity gain buffer. This again serves as a high impedance to low impedance buffer in the circuit. And generally, the voltage at this output is going to remain fairly constant as long as the input square wave remains fairly constant as well. There's a little bit of fluctuation as the capacitor does discharge slightly in between sampling intervals, but as this is on the order of milliseconds, it kind of averages out over time. The same circuit is present on the current measurement side, where we have a switch, we have a sampling capacitor, and then we have a unity gain buffer. Everything after the unity gain buffers is the ADS1115, this standard 16-bit ADC that we use for pretty much everything else. And this whole circuit takes 2 inputs of the ADC, leaving 2 remaining inputs for other purposes.
All right.